In today's lesson from section 7-4, we're going to take a look at a postulate for similar triangles. So we've learned how to prove whether two polygons are similar by showing that all pairs of corresponding angles are congruent and all pairs of corresponding sides are in proportion to each other. But that seems like a lot of things to prove when it comes to just showing that two triangles are similar to each other. So today and tomorrow in class, we're going to take a look at a few shortcuts. So postulate 15 states that if two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. That's it. It's a shortcut. All you have to do is prove two pairs of angles congruent to each other. And we refer to this as the AA similarity postulate. So let's take a look at a proof that uses this postulate. So it's a basic proof. It's just going to be 3 steps. Of course, our first step is our given information that line segment AC is parallel to line segment BD. So go ahead and mark those two line segments parallel to each other in your picture. So AC parallel to BD. Okay, we've got parallel lines. We have our midterm exam coming up, so this is a great review question. So when two parallel lines are cut by a transversal, such as this transversal right here, we know that we have alternate interior angles that are congruent. The same thing is going to happen along this other transversal, though we get another pair of alternate interior angles that are congruent. So in step 2, let's name those pairs of congruent angles. We have angle A congruent to angle B, and we have angle C congruent to angle D. And again, we can write this in shorthand notation, the reason would be if two parallel lines are cut by a transversal, then alternate interior angles are congruent. Okay, I need to move this up just slightly to finish off our proof. And according to the angle-angle similarity postulate, we have enough information to conclude that our triangles are indeed similar. So in our third step, we can go ahead and say triangle AOC similar to triangle BOD. Be careful, because we spent so much time working on proving triangles congruent, your brain is going to want to write a congruent symbol here, so watch out for that. These two triangles are not exactly the same size and same shape, so they're not congruent, they're only similar, meaning, again, corresponding angles congruent, corresponding sides proportional. Okay, to justify the fact that these triangles are similar, all you need to write for your reason in step 3 is AA similarity postulate. We're using the angle-angle similarity postulate. This is just one of our possible shortcuts. We're going to learn a few more tomorrow. So next, we're going to take a look at another example of proving triangles similar. Oh, and by the way, just like when we prove triangles congruent, the order in which you name those triangles is important. So make sure that the vertices line up so that the corresponding angles are congruent. Angle A is congruent to angle B. Angle O is congruent to angle O, well that's our vertical angle, and angle C congruent to angle D. In our second example, we start off with a kind of funky diagram, and you notice in here we have two right triangles, and we don't start off with right angles, but we start off with perpendicular lines, which will give us right angles, and we can easily prove that they're congruent. Notice that what we're trying to prove, though, looks a little funky. We're not just trying to prove two triangles similar to each other. This statement that the length of line segment HR times the length of line segment BF is equal to the product of the length of line segment BA times the length of line segment HA actually comes from a proportion. Imagine if you first saw this proportion, HR over, not BF, but over BA equal to line segment HA over line segment BF. All right, we could write that proportion if we could prove the triangles similar to one another. Because if our two triangles are similar, then we can say the corresponding sides are proportional. So HR, this side, would correspond to line segment BA, this side. And line segment HA, this little piece, would correspond to line segment BF, this piece. Okay, so we have to prove the triangle's similar, then we have to set up a proportion, and then we have to cross multiply. Okay, so we've got a lot to do. In step 1, go ahead and say that line segment AB is perpendicular to line segment BF, and line segment RH is perpendicular to line segment AF. We know this because it's given. We love that given information. Okay, there's a lot we can do with that. I'm going to kind of step it out for you, and we're going to say that angle RHA and angle FBA are right angles. Because that's one of the basic things we can get out of perpendicular lines. That's just by definition of perpendicular lines. If two lines are perpendicular, then they intersect to form right angles. Okay, in step 3, we're going to go ahead and say that angle RHA is congruent to angle FBA. Now, in some textbooks, they would have you say first that each of those angles has a measure of 90 degrees, and then you could say that they're congruent because it's the definition of what congruent angles are. They have the same measure. In this case, we're going to justify this by saying just simply all right angles are congruent. Okay, just keep in mind that every textbook, every kind of presentation does things a slightly different way. And what I'm telling you, my students in honors geometry, is that this is okay to take this little shortcut here. Okay. In step 4, we're going to go ahead and say our other piece of given information, angle 1 is congruent to angle 2. And that was given to us. Technically, we could have included it in line 1, but you know how I like to set things up and kind of separate out the given information. So here's angle 1 congruent to angle 2. Our right angles are congruent. We have similar triangles, so we can say that in step 5. And be careful when you name it. Name the triangles. I named the first triangle, triangle RHA. And it's similar to, watch that, make sure you don't say congruent to, but it is similar to triangle ABF. Notice how when I named this, I went from R, or angle 1, down to the right angle, and then out to A. So follow that same pattern in the second triangle. Go from angle 2, because that's congruent to angle 1, to your right angle, and then out to F. Okay, these two triangles are similar by the angle-angle similarity postulate. And then we're going to take it 2 steps further. In our next step, because the two triangles are similar to each other, that allows us to write the following proportions. Okay, we're going to compare all of the sides. So I'm going to keep this in mind. I'm going to go in that order, HR. So I'm going to compare HR and from my first triangle to BA from the second triangle. So those corresponding sides have that ratio, and that would be equal to HA, the middle and last letter of the first triangle, to BF, which would be equal to, finally, RA, first and last letter of the first triangle, over AF. And this is an F right here. Okay, this is the reason to justify it is the fact that corresponding sides of similar triangles are in proportion. Okay, I scoot this up. We're going to finish it off with our last step here, number 7. All we have to do is take these two ratios and cross multiply. We don't need this one at all because it's not included in our given information or what we're trying to prove. We just have to prove, sorry about that, choose the right setting there. We just have to prove this right here. So those first two ratios that we have, we're going to do the product of the means equals the product of the extremes and come up with our proof statement. So cross multiply and take HR times that BF. So we're going to say the length of line segment HR times the length of line segment BF is equal to BA times HA. Now you could actually say the product of the means equals the product of the extremes to justify this, or you can be a little bit more general and just say that this is a property of proportions. Okay, good luck on your homework tonight. As always, email me if you have any questions or come and see me for some extra help.